Okay. Okay, so I'm Josh Susskind. I'm a co-founder, like Marnie, of Emotient, and I've been working as a data scientist for a few years there, and have been involved in all sorts of things. And one of the areas that's really kind of very important to me is employing feature learning to within deep nets and other kinds of approaches to improve our emotion recognition, detection, accuracy, and so forth. So I'm going to talk a little bit kind of more broadly, why is facial expression recognition important? So this is really a motivating question for why is it that we would want to develop these kinds of systems? So for one, it provides a direct response to stimulus. So for example, in comparison to EEG, where you might hook up a person with a bunch of electrodes to measure something indirectly related to their mental state, why not just look at their face and get a reaction and quantify that reaction over time? So that's one area where we think automating the process of recognizing facial expressions could be really important. And having tools like webcams and cloud-based services, we can then employ this at a large scale in a cost-effective manner to analyze people's behavior. And this can then be done in anywhere, anytime, using a non-invasive measurement technique. And we think then that would allow us to explore applications in marketing, healthcare, education, games, all sorts of areas. But why is facial expression recognition a difficult thing to do? What makes it hard relative to other computer vision problems? Well, for one, people are really good at it. This is something that everybody from a very, very young age learns how to do. Of course, some people aren't very good at it, but most are. And because of that, people aren't very forgiving when a system makes a mistake. They notice it. And in particular, small mistakes like mistaking a yawn for surprise, which to the system, they look very similar. The actions that are going on those two faces are very similar. But the mental states that underlie those two expressions are very different. You wouldn't want to mistake them for each other. So basically, in a situation where people are yawning because they're tired, if you think that they're surprised and interested by the information, that's actually an incorrect assumption. And so we don't want to make that kind of mistake. Also, expressions are easily masked by factors like the face pose. So like in this example here, you can see that at the top, this guy's making a surprise expression the whole time, but as his pose is varying in a non-planar way away from frontal, the features that define his surprise face are completely changing across the image. So it's really a very large-scale global change that's affecting the features of interest that you'd want to be able to quantify as surprise. And so other factors like identity, that's another case where people's facial features might be in kind of different places, and you'd like to develop a system that could be robust and invariant to these kinds of displacements. So as covered, I think, numerous times already here, so in computer vision in general, and in expression recognition in particular, the field has been dominated for a number of years, 10, 20 years, by engineered feature approaches, like employing Gabor filters as a first layer of feature processing to the image, in which case a lot of thought goes into how you engineer these features. And then in most of these systems, the outputs of the system are essentially a linear combination or weighted sum of the filter responses, which is really the filter responses are the only nonlinear aspect of the system. And then the only stuff that gets learned directly in this sort of approach is the weights between the filter outputs and the prediction that you're trying to make. So for a long time, these kinds of approaches were actually quite good for cases like frontal face expression recognition, when the lighting is good in a laboratory setting. So for that, that's fine, but we're interested in doing expression recognition in the wild. Like, for example, here, I can see everybody, and certain people are facing me, but then the people on this side or over here are not completely frontal with respect to where I'm looking. And so I'd like to have a system that would be robust and still perform roughly the same, independent of those changes in pose. So this kind of system basically is defined by its limitations, these template matcher kind of systems. So back in grad school in Toronto with Geoff Hinton and also my co-advisor in cognitive neuroscience, I was very interested in employing feature learning strategies to combat the problems of these hand-engineered systems. And so early on, this is actually reminiscent of Charlie Tang's talk. So at the time, this was the first deep learning approach for facial expression recognition. We used a deep belief net. And I think this actually may have been the first or one of the very first times anybody had actually tried such a model with real valued high dimensional inputs. Most of the work up to that point had been done with MNIST, and I think there was one paper, actually I think it's the 2006 paper with Russ Salakudinov, where they had faces varying in, I think, the tilt of the face. But that's about the only paper at the time that had looked at anything related to face representation in multi-layer neural nets. And so at that time, what I was interested in doing was seeing if we could both generate and recognize expressions and expression configurations in the same net. And so this network had actually two kinds of labels. One was the face identity. And so this was basically just a softmax code over 150 or so identities in the training set that we collected. And then a set of 8 expression labels. And these expression labels were actually facial actions, so like raising or lowering the eyebrows, smiling, et cetera. And what was really neat is we could basically clamp the labels that define the identity and expression and then pass basically up to the top layer associative memory of the deep net, and then back down to generate samples that would correspond to what the model believes about the association between the labels and the expression. So this was kind of neat. It was the first time that you could sort of inspect the model's beliefs about how faces associate with labels. And conversely, we could start from the image and go up through the layers to the top layer memory and let it settle into a set of expression or identity labels that defines recognition or expression recognition. It worked pretty well, but over the years since that time, a lot of work has gone into much better recognition systems. This is really sort of a proof of concept at the time. So another variant of this technique was to explore modeling the relationship between pairs of images. So I was very interested in models that could extract essentially the way that the pixels transform in a face from, say, a neutral expression to a joy expression, and then capture this relationship in the hidden layer of a gated Boltzmann machine at the time, and we've since done some work in gated autoencoders to do the same kind of thing, so that the hidden representation captures essentially the transformation between the pairs of faces. And then what we could do is we could apply the transformation extracted from the pair that it sees at inference time to infer the transformation, apply that to a test person that it had never seen before, and then show how the network could then transform the features of that test person to match the endpoint of the expression inferred from the previous pair. And so what we could do basically with that is something like face puppetry, to show basically like have the network look at a sequence of expression changes from one face and then generate on another face what those expression changes should look like, simply by capturing those relationships in the hidden configuration. This is kind of neat, and again, I've sort of been watching the literature in the last few years. There's been a lot of work in this area of basically sequence modeling and factoring the content of the images from the way those images transform, and the results are getting better and better and cleaner and faster. It's really exciting to watch. So in particular, going back to standard vanilla expression recognition, so recognizing expression label from an image, I just wanted to sort of highlight that a lot has happened in the last few years, 3 or 4 years, and in particular with deep learning. And one of the reasons that there's been a big change is that new data sets have emerged, much bigger data sets than what computer vision community was using previously. So I think the early explorations in computer vision used images, basically sets hundreds to a couple thousand labeled samples. So in Jeff's lab, I introduced the Toronto Face database in 2010 that contained about 100,000 labeled example, or labeled plus unlabeled examples. This was really the first data set where people started really looking at models of faces in deep nets in a kind of way that they could track performance over time and try out different techniques. So at the time we introduced this set, our baseline accuracy was at about 74%, and that was in 2010. So as of 2014, the best I could find in the literature on this data set is now up to 88% accuracy. So you can see that on the same set, just variants of deep learning models are now getting much, much better and almost approaching ceiling on that data set. So we recognized this at Emotient pretty early on and realized that if basically our interest is in being able to do expression recognition in the wild, we need a very powerful learning system behind our computer vision pipelines to be able to focus on these difficult problems. So we're we make strong use of deep learning. So remember, our goal here is to build a very, very accurate system that can adapt to all these different situations, but it also has to be really fast. So I'll talk about that a little bit. So here's just a slide showing the initial impact of applying deep learning on our recognition pipeline for expressions. So first I'll show you basically CERT. CERT was the name of our academic product back in 2011, 2012, where we were getting about 72% accurate. When we pushed to commercialization, before we had actually switched to deep models, we jumped that accuracy up to about 86%. So that's a pretty big jump. It's about 49% error reduction due to commercialization, but that involved massive data set curation. So there's a big jump to collecting much, much more data than we had available at the time we were academic, and also about a year of refining algorithms. So on the right, what you see is the jump in accuracy simply from introducing a new architecture. So the previous architecture, which wasn't deep, got about 91% accuracy in the latest iteration. Our first iteration of a deep model using exactly the same training data led to a 40% error reduction. And basically, this is amazing because if you look, the accuracy is already starting to hit ceiling on our data sets. And by the way, these data sets are internally curated data sets that we use both to train and evaluate our system. And they were intended to be basically reflecting the kinds of variations that you might see in the wild. So very difficult pose ranges, lighting conditions, and many, many examples, hundreds of thousands to millions of examples. So the changes that we saw weren't restricted to particular configurations or labels, but we actually found even for the simple recognition problems like joy, moving to a deep architecture improved our accuracy significantly. And this is important because as a company, we're developing new channels all the time, so recognizing confusion, frustration, component actions, and we want to have an architecture that can, across the board, improve our performance as we focus on collecting more data and tuning the algorithm. So in addition to simply just looking at how our accuracy overall changed with a new architecture, we're happy to see that simply changing the architecture to something that could deal with a number of different configurations mapped to the same label, simply by doing that, we were able to keep our accuracy very high, even as the range of yaw of the face goes out to about 30 degrees, which is about the range of our pose detector at the time that we made this graph. So basically, the entire range that the face is detected, the accuracy in expression recognition stays up near above 90%. And that's relative to our previous system, which degraded steeply as the yaw of the face went away from frontal. Similar, we see a similar effect with pitch. Here, for 4 of the sectors of pose space that we're mapping here, the accuracy stays above 90%. We have one area that we're still looking to improve, which really has to do with being able to collect enough data in that kind of situation, so the looking down situation. But we can still see that our accuracy overall is improved even for that range using a deep model. So I'm not going to tell you too much details about our architecture, mostly because I don't have too much time, but I want to mention that one of our biggest concerns is being able to deliver results very quickly. So we need to be able to employ our recognition in real time, so 30 frames a second basically, from as many faces are in the image as we can possibly manage, right? So if you have, let's say, a 640 by 480 image and there's 8 people in that image, we need to be able to return a result in roughly real time. So we can't rely on these kinds of techniques that might use, for example, large-scale GPU acceleration that is optimized for batch mode. We need to be able to return a result for an image almost immediately. And our architecture needs to be able to run on a range of different form factors, from CPUs and laptops to mobile devices to embedded systems, and as well as on the cloud. And of course, when a GPU is available, it's of course great. And if we can run a video in batch mode, then we definitely make use of that. But what I wanted to sort of convey here is that over the last several years, we put a lot of engineering work into optimizing a end-to-end system all the way from face detection through emotion recognition using deep learning that's able to achieve that turnaround time. So it wasn't simply an off-the-shelf classifier. So here's just an example of from an in the wild case where this was basically Super Bowl, a group of people from Denver and Seattle fans from Super Bowl last year watching the Super Bowl in a theater, and we're capturing their response to a series of 3 ads while they're watching the Super Bowl, and basically returning their results in real time back. Oops, see if I can actually show it. Okay, so at the beginning of the ad, what's happening is Stephen Colbert is showing up, and everybody at first is kind of like, yeah, what's going on here? You see a little bit of joy. Everybody starts to smile because they like Stephen Colbert. And then partway through the video, David Beckham comes in on a zip line, riding in on a zip line in his underwear. And people are just kind of like confused and grossed out, and you start to see a lot of expressions that aren't just joy happening, which I think was reflecting the kind of confusion and disgust that they have with this interlude. So near the end of the video, Stephen Colbert comes back in, and you see joy return to people's faces, and essentially you get a big joy response at the end. Advertisers are very interested in capturing this kind of emotional journey, being able to track the response of an audience as they're watching an ad or a movie trailer, that sort of thing, in a natural environment. So we show here that we can deliver that kind of information back to advertisers, for instance. So I just wanted to conclude by restating, of course, that we know that expression recognition in the wild is a very difficult thing. I think computer vision in general in the wild is difficult. And so we employ deep learning in a number of different ways to deal with that. But we have the problem that runtime speed is essential. And in the literature, I haven't seen that much to date on really focusing on that problem outside of the kind of work of focusing attention and sort of maybe using much smaller, low-resolution glimpses, for example, to be able to return results fast. But even so, a lot of those kinds of techniques rely on batch mode kind of processing where you have a bunch of images that you're looking at once. And so we need to be able to develop these kinds of systems that can respond in real time, accommodate a number of different form factors. And I think that's an interesting challenge in the years to come. And as I said, expression recognition has a lot of applications, and we're really excited to be pursuing them. So check us out, we're at Emotient.com, and thanks.